I want to briefly talk about a topic related to Thevenin equivalence, and that is maximum power transfer. So in the circuit here, I've got a Thevenin equivalent V sub t and R sub t, and now between the load terminals, I've connected this resistance RL, a load resistance, with this diagonal blue line across it. And so this line indicates that the resistance has a variable value, and that could represent something like a potentiometer where we're changing a dial or a knob and the resistance is changing, or it could simply indicate that we are physically taking a resistance out and putting in a new resistance in the circuit. But again, in the paper representation of our circuit, we can just say that our resistance is changing. And so it turns out that our maximum power transfer to that load occurs when our RL is equal to RT. And so I'm not going to go through the full derivation of that, but you can see that on page 101 in the textbook. Essentially what we do is we calculate an equation for the power of this load resistor. We then take the derivative and we set it to 0 to find a local maximum. We could use our circuit analysis techniques to figure out the voltage across this resistor or the current through it. We could then use our power equations in a resistor, V squared over R, I squared R, or I times V, and we would find that our PL max is equal to the Thevenin voltage squared divided by 4 times the Thevenin resistance. So that's the maximum instantaneous power that our circuit could provide to a load. So it's very important to note, though, that maximum power transfer does not equate to maximum efficiency. And so there's a good problem, P2.93, in the textbook that goes through that numerically.